Well, what we're looking at here is a Fluke 1952A digital counter. This particular unit will measure up to 512 megahertz on channel C, which is here, and 80 megahertz on either channel 1 or 2, channel A or B. We can measure frequency, period. We have a totalizer. We can choose to gate channel A from B, so we compare the two. We have a self-check position. We have 6 gate times going from 0.1 milliseconds to 10 seconds. And we have a cycle rate, which is sort of like a gate time in that we force an update to the process up to the point to where the gate then becomes the major stumbling block. In that case, the gate takes over. We have trigger level controls to position our what would that be? This would be our shot key trigger points. So like there you just saw the positive edge disappear, and we got the negative edge disappear, and then we're centered properly when both are lit. And that's when I'm going to get my most accurate reading. We can change the slope, we can change the attenuation from ×1 to ×10. This unit also has a computer output on the back, BCD output. We have an external output. We have external gate channel in the back. Let's see if I can turn this whole thing around so you can see it. It's a nice looking unit. It's not extremely large, not extremely small either, but kind of a nice size. We have a gate input, a marker, clock output, external reset. Here's your BCD output, external 10 megahertz clock. So you could run this thing off of a Rubidium, which I've done on my bench at times. And like I said, we have on channel C, we can measure up to 512 megahertz, which is nice. We have a 7-digit display, and as we turn up our, or I should say turn down our gate speed, right now here we're reading 10,000 megahertz, so add 3 zeros to it, you got 10 megahertz. If I go to 1 second, the 1 slides off to the left to a place where we can't read it, and then we're left with well, in this case, the thousands place, the hundreds, the tens, the ones. So let's try that again. Million, hundreds, thousands, 10,000s, thousands, hundreds, tens, ones. And then if I go to the 10-second average, we shove everything over one more time, and we'll get the 10th of a hertz. So right now we're reading 10 megahertz, accurate to, in this case, the first reading, it says half a hertz, so within 0.5 hertz. And I think it's basically keeping that time. Yep, half a hertz. So we go back. Here we are at a 1/10 of a second gate time. We read 10 megahertz right on. It's a very, very nice counter. Make a very nice addition to somebody's bench. We'll take a quick look at the outside of it. Heat slots. It's kind of a leather wrapped case. A medium blue color, black faceplate. Nice shiny faceplate. Not much in the way of scratches or anything on it. Very nice. And basically would do just about whatever you would need it to do. We can ratio A to B, time intervals A to B, and so on. So we're going to run this thing through its paces real quickly just to show you that we can read accurately on the channels, and then we'll go. We'll belabor this thing. Alright, at this point we've connected ourselves up to this PTS 500, and the PTS is in itself connected up to my Rubidium standard, which is the dark black box in the back, and coming through this Fluke distribution amplifier. So I'm using that Rubidium as the master clock for my PTS, which gives me very accurate signals. No matter what I dial in, I can synthesize accurately. So we're reading right now 10 megahertz on channel C, and we can see that we have 10. Let us go 20. You kill the light in here. See if that'll help me. Maybe it's the overhead. Well, that's a bit better. There's 20, 30, 40, 50, 60, 70, 80, 90, 100. Now, to see 100, I've got to cut my gate time, or raise my gate time up by a factor of 10. Here's 100 megahertz. There's 200, 300, 400, 490, 499, 499.9999. There's 500 megahertz right there. No problem. And I believe we could actually go much higher. I just can't produce signals much higher. This is my my fastest generator. So there you have that. Let's then go to channel A, and we'll go downwards instead of upwards. All right, here we are at 90 megahertz. Let's go 80, 70, 60, 50, 40, 30, 20, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 900 kilohertz. Let's go ahead and kick our resolution up a little bit by dropping our gate time, or expanding our gate time. We're now going, I think we're at 0.1. So there's 900 kilohertz. Let's go 800, 700, 600, 500, 400, 300. Don't know if we can go any lower. 300, I think, is it. We're going to have to move to a different generator at this point. And we're going to use this Hewlett-Packard 3320. And we're going to pick it up at 100 kilohertz. 90, 80, 70, 60, 50, 40. I think we can go up. Yeah. There's a 1 second gate time. We'll update every second. That's not too bad. 30, 20 kilohertz, 10, 9 kilohertz, 8, 7, 6, 5, 4, 3, 2, 1. Alright, here's 900 hertz, 800, 700, 600, 500, 400, Okay, we're at 400, 300, 200, 100. There's 90, 80, 70, 60, 50, 40, 30, 20, 10. Nine, 8, 7, 6, 5, 4, 3, 2, 1 hertz. Let's go to the 10-second average and see what we got going on. I'm at 0.9 hertz right now. See what she does. It's 0.9, 0.8, 0.7, 6. I'm in DC mode right now. And we'll go to 0.5. I'm not even going to bother to go lower, but it's interesting. There's 5. Alright, let's go ahead and switch to channel B. Alright, well, we've connected our 10 megahertz Rubidium to the A input. We have our HP 3320 connected to the B input. We're feeding 5,000 hertz into B, and we've got 10 megahertz going into A. We are in the function of A to B right now, so A over B, so 10 million over 5,000, and we're getting a result of 20,000 counts. If I was to go to 4,000 hertz on B, we should go to 250,000, or excuse me, 25,000 counts. And we are. If we go to 3,000 hertz on the B input, we got 33,333 would be the perfect, and that's basically what we're getting. So the B input is working as well, and our ratio is working as well. So there you have it. I've given you an example of what this thing can do with it. I'll give you a set of test leads with it. So happy bidding. Thank you.